Hello everyone, it's a pleasure to be here to introduce our midterm project. We are the group of interest finder. Our project topic is keyword search on structured database. So let me give a brief introduction first. We are in the track of data discovery, and we are interested in how to retrieve information of users' interest. There are lots of cases that we do not know the schema, or the schema is very complicated that the users could not remember it. And there are also situations that when we search for something, we want to find out the relation link to that kind of thing. For example, if we search for a person, we want to know its location or its belonging organization. For example, if we search for Steve Jobs, we need to know where he is and what organization does he belongs to. And this kind of information may be separate in other tables. So we need a new way of searching. And what is the difference from the traditional database query of our setting? So the first of all, we do not need any schema knowledge, and we can automatically join back all the tables that are related to this kind of keywords. For example, if you search for Steve Jobs, you may want to get back some location information that's stored in another table. So we have to join back this kind of two tables to get this information. And of course, we want to provide a ranking of the results. Our input is like the keywords. So we only have keywords as the user's interest. And the output is a ranked list. It looks like this. If we search for Michael Jordan, it will output all the Michael Jordan in a ranked way. And if you notice, there are some attributes that may come from other tables. The Yahoo dataset only consists of numbers, and since we are dealing with search, it's not reasonable to search numbers because if you search for 0, then it may be containing lots of numbers, right? So it's not good for searching. So we instead use the Yago RDF data. The data set looks like this. So for each row, it contains 3 values: the subject, predicate, and the object. For example, it may contain a row like Steve Jobs works for Apple company. So in the following, I'm going to talk about what we propose in the solution. So first of all, we need to model the data as a graph. And because we're using RDF data, it's very natural to model it as a graph. But I want to say is even with relational database, like these are all tables, we can still model this as a graph. And these are the links that the links here are just a foreign key from the relational tables. So the second step is to build up keywords index and graph index. These are two kinds of different index. So why do we need keywords index? That's because we are only searching for keywords. We do not search for a phrase. So if we have some kind of entities like University of Illinois, we have keywords index on this entity like University and of and Illinois. And we need to incorporate traditional IR techniques into this. For example, we need stemming. We need to stem the two kinds of words into only one. For example, if it is a word of run and running, so these two words should be indexed as only one. And we exclude all the stop words like of and the and something like that. And also we need graph index, and this is needed because we need to find the links, and this is very useful for ranking. And the third step is to map all the keywords to elements on the graph. For example, if you're searching for jobs, it may be mapped to values like Steve Jobs, or it may be mapping to nodes, like if you have a table of a person, a node may be the attribute in the schema, like job. It may also be mapped to edges. For example, if you have Michael Jordan has the job of basketball player, so it may be mapped to this kind of semantic relation. So the fourth step is to, based on the mapping, retrieve back a subgraph with ranking function. For example, if the graph looks like this, it may be very, very large, but after search, it may be mapped to a certain number of nodes. So based on these nodes, we want to retrieve back some subgraph that contain all the keywords. So for example, we have two graphs, and they have two scores based on how this subgraph is like. So how do we rank? This is a very key problem in our model. So we have some intuition about ranking right now. So want to consider the similarity, that because it's like if we search for some keywords, is it contained in exactly the keywords, or it is ambiguous inside that entity? So we want to consider whether it is similar or not. And the second one is authority. Is some kind of like the PageRank algorithm. It's like if you search for an author like Jiawei Han in a DBLP dataset, so it may be mapped to lots of authors, because some author may also name Jiawei, and some author may have the word Han, but you want to retrieve back the author that published a lot of papers, or he published a lot of paper to a very famous conference. You want to give higher rank to those authors, so you have to consider authority. And the third one is you have to consider when retrieving back the subgraph. So what's the distance between each node? It may be very, very long, the distance, so we need to give a penalty on that kind of situation. So the subgraph, after the ranking, we need to retrieve back a subgraph. So the subgraph is, we have to retrieve the subgraph that contains all the keywords, and we need to make it as minimal as possible. This is a well-known problem of Steiner tree. So although it's NP hard, we can find the solution using A* search. For example, we can use heuristic, like we can map this kind of instance graph to the schema graph, like Apple we map to company and file system map to software. We can find the distance on this graph, this kind of graph, and this graph is very small, so it can be maintained in memory. So we can see whether these kind of things are very distant from each other. So if they are very distant, we can prune that, so we don't need to do any computation on that. So let me show all the preliminary results. So right now we have completed 3 steps. The first 3, we have built a graph model. We have index on the node and on the edges, and we have done a simple mapping back to the nodes with a simple search. So these are the a sample result for if we search for Apple. So this is the key we assign to this entity, and this is the entity we map to. Like this is a value. So we have completed 3 milestones, just as what I said, and we still need 2 more. Like we need to rank all the subgraphs. We need to implement a ranking algorithm, and we need to visualize the result in a web page or somewhere else. So let me do a quick demo. So right now we have 2 classes. The first class is building index. So we have already built that, so we don't need to demo anymore. And this class is to search. It's a very simple mapping. Like we map Apple and company back to the graph, and we get a result in a file. So let me run it first. And by the way, so all the index right now is local, and our data is also local. But we will upload that to the Hadoop later, and that won't cost too much change, because basically the algorithm should be the same, but maybe retrieving data should be a little bit different. So if you can see, while I was talking, the algorithm already stopped, so it's very efficient to retrieve. So let me show the result. So let me give a brief explanation. So if we search for Apple, these are just what we have said, what we have seen. These are these on the right. These are the edge that link to this entity. So these are the keys that we can find out using the key. We can find out all the entities that link to this entity. So it's very, very large. And at the bottom we can find some results for the company also. Okay, I think that's all for the presentation. Thank you very much.